Hello and welcome to this chemistry lecture series. In this video, we're going to look at chapter 10.8, which is going to deal with a bit of an unorthodox approach to sections. We're not going to look at any reactions or anything like that. We're going to look at how to approach questions in the AICE chemistry exam. This is going to focus on deducing the position of the elements in the periodic table, something you actually got to do a lot in the AICE exam, where they give you scenarios and you have to use your knowledge to figure out what a specific element is, or at the very least, what group it's in. So let's start here. Now, deducing the position of an element is an ability that you should really have if you want to get an A or a B in the AICE exam, because it's something that you're definitely going to encounter, not just with this chapter, but with all of the chapters in inorganic chemistry, so 10 through 13. We can use the trends that we learn both in physical properties, but also in chemical properties to identify unknown elements. This happens a lot, not just in paper 2, but also in paper 1 when it comes to the Cambridge exams. In some cases, they won't give you a specific period, and you have just to identify an element based on its group. So you could say it's a group 2 metal or a group 1 metal. Sometimes they'll give you the period, and they'll tell you it's a period 3 element. And so as soon as you know which group it's in and you deduce what group it's in, you'll be able to identify the actual element from that deduction. This does not only go in the way that they ask you for what the element is, but in a lot of cases you'll have to actually explain the trends that you're using and explain the periodic properties for those elements and how you came to that conclusion. This is obviously a lot more common in paper 2 than paper 1, as explanations are usually a 2 or 3 point question. So let's look at some example questions here. So this is a very common type of question where they'll give you a graph of a specific property, and you need to use your knowledge to deduce either which elements which, or which could be a specific element. So here they tell us we have a diagram of melting points. When approaching these questions, it's always important to identify what this is a graph of, which of the many properties, both physical and chemical, that we have discussed and that we will discuss. So in this particular case, we're looking at melting points of 8 elements with consecutive atomic numbers. And this is very important. With consecutive atomic numbers means that they are next to each other on the periodic table, or they could be the end of one group, the beginning of the next. So as we look at this, the question becomes, which of these elements could be sodium? So when we think of sodium, right, we're thinking of a few things. We're thinking of a group 1 element. We're thinking of a metal. We're thinking of a +1 oxidation number. So these are some things that we need to keep in mind. We're thinking of giant metallic structure. So, looking at this, they're giving us 4 choices, and you might not have noticed this, but if we look at this chart, there's an A, B, C, and D on the chart itself. And so our options, these are essentially our multiple choice options, A, B, C, or D. So one of these has to be sodium. Now, looking at our chart, we gotta see a few things here. First of all, let me change my color here. The melting point from A to B decreases. It drops from A to B. Now, if we remember what we discussed in earlier chapters and earlier in this chapter, we got to remember that as far as melting point is concerned, things with simple molecular structures have the lowest melting point. Whereas metallic compounds are going to have a higher melting point, as well as ionic compounds. And then at the very top of everything, is going to be giant molecular or giant covalent. Well, if we look at these, we can automatically eliminate ionic as a choice because we're looking at elements, and elements can be ionic, only compounds can be ionic. But this logic means that if we're looking for sodium, which is a metal, we're looking something along the middle of the range. If things are going down, that means that either we're going from giant covalent to metallic or metallic to simple molecular, meaning that B automatically gets eliminated as a choice, being the lowest of the four choices. It probably is something that's simple molecular. And then after that, they start going up. Now, within the realm of metallic, we got to remember that the melting point is going to increase for a higher charge. So +1, +2, +3. So even though that sodium has a fairly high melting point because it is a metal, it is only +1 metal. The metal next to it, magnesium, is a +2 metal, and the one after that, aluminum, will be a +3 metal. Before sodium on the prior end of the periodic table, we have a noble gas. We have neon. Neon is a simple molecular structure, so this is a very low melting point. Whereas sodium, magnesium, aluminum, the melting point is going to increase as we move from sodium to magnesium to aluminum. So if we were to actually draw this graph from scratch, not taking into account the graph they're giving us, we know neon has a very low melting point, so it will be very low. We know sodium will be higher than that because it's +1 metal. We know magnesium will be even higher than that. So this is Na. No, sorry, oops. This is going to be not Na, but Ne. This is Na. This is Mg. And aluminum, being even higher charge, +3, is going to be even higher melting point. So when we look at this, we have an increase. Sodium will have to be the second in an increase of charges. If we look at our choices, this section right here matches what we're seeing. We have the lowest, which we had already eliminated as probably being simple molecular. That's probably going to be neon. We have the one right after that, which is a little higher. That's probably sodium, then magnesium, then aluminum. This little section that we're looking at here matches our increase. And if we think even more, before neon, we have fluorine, which is the F2, the diatomic molecule. Fluorine will have a fairly simple molecular, but it is higher in number of electrons than simply neon, giving it a higher melting point. So this right here makes sense. It makes sense for this with fluorine, neon, sodium, magnesium, aluminum, because the pattern fits. Fluorine, being F2, would have a higher melting point than neon, but a lower one than sodium, because it's still simple molecular. Sodium will have a higher one than those two, but lower than magnesium and aluminum, which are also metallic, but have higher charges. Meaning that the only possible answer here would be for the correct answer to be C. And that is indeed our correct answer. So you can see, like, I had to explain this a lot, right? But if you actually internalize all of these patterns, all of these trends, and that's what's important why you're taking your notes, to look not just at what's in front of you, but at the trends between elements. It's something that you should be able to figure out without having to undergo this whole logic. I am obviously teaching here. I am trying to point out all of the different patterns as we go through this, and that's why I'm showing you all of this. But it is a really high-level critical thinking question, because you got to put a lot of different facts together to arrive at this answer. So here's an example of a paper 1 question that you could see. Let's get another one. Another example of a paper 1 question like this one uses, instead of physical properties, chemical ones. The question we just saw earlier used physical property, melting point, but this one uses chemical reactions to essentially do the same thing. So if we read this, element X is in period 3. So we know element X is in period 3, meaning that it has to be either sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, or we're going to actually leave out the noble gas because it's never the noble gas. Element X in period 3. Element X forms a solid oxide. So solid oxide meaning that when this element reacts with oxygen, the compound that it creates is solid. That is going to eliminate Cl, because chlorine does not actually form compounds with oxygen. We talked about it earlier. Sulfur dioxide, so trioxide gases. Phosphorus oxide is, or P4O10, it's a liquid. So the only ones that we have left are sodium, magnesium, aluminum, and silicon. That mere fact that it forms a solid oxide eliminates 3 of our choices already. So if we keep reading, so why is a solid oxide? And it's very important to keep track of these letters here. So we could do this. We could put right here X equals element, Y equals element oxide. So the compound. So then if we keep reading, Y reacts with hot concentrated hydrochloric acid. So this might just seem like a reaction to you. You might look at this and say, okay, it reacts with HCl. Got it. But think about the wider topic and the trends. If Y reacts with concentrated hydrochloric acid, if it reacts with an acid, that means that Y has to be basic. Because if it reacts with an acid, it has to be a base. But if we keep reading, Y reacts with hot aqueous sodium hydroxide. Sodium hydroxide is an alkali. Sodium hydroxide is a base. If it's reacted with a base, that means Y has to be an acid. Well, how can it be both, right? How can it be a base and an acid? Well, that means that Y, the oxide of this element, is amphoteric. It reacts as both an acid and a base. It says to form a compound in which X is part of an anion. Now, this part isn't necessary for us to answer the question, no, but it does make sense, and I'll show you why in a second. But let's go back to this. The element oxide of this element X is amphoteric. Out of all of the period 3 elements that we discussed in this chapter, only one of them was amphoteric. The only compound that had an amphoteric oxide was aluminum. Aluminum is the only element that had amphoteric oxides, meaning that element X has to be, and let me actually put this in a different color, element X has to be aluminum. And the element oxide, therefore, has to be aluminum oxide, Al2O3. Why? Because aluminum oxide is amphoteric. It's the only oxide of period 3 element that's amphoteric. Not only that, if we go back to this compound in which X is part of an anion, when sodium hydroxide reacts with Y, with the aluminum oxide in this case, X is part of an anion. Aluminum is part of an anion. If you remember the reaction, when Y, or when aluminum oxide reacts with sodium hydroxide, it creates NaAlOH4. In this compound, sodium is the cation and AlOH4 is the anion, which is AlOH4 minus, which is the anion we saw when we were studying this reaction. So this further clarifies that X has to be aluminum, because this is the anion that it creates when it reacts with sodium hydroxide, and it says here to form a compound in which X is part of an anion. The aluminum is part of an anion. So we know X has to be aluminum. Great. And if the question was, what element is X? We would answer aluminum. But it's a more complicated question even. If we keep reading, how many p electrons does one atom of X have in its outer shell? So now it's even more complex, right? Because we're not just talking about what is it, it's aluminum. We are now talking about aluminum's electron configuration. Aluminum has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p1. How many p electrons? So how many electrons are in p sublevel does one atom of X have in its outer shell? So we're looking at the valence shell, which is energy level 3, and we're looking at the p electrons of the valence shell, which is the 3p sublevel. And it tells us how many electrons are there. Well, there's only one electron in the 3p, in the highest energy level outer shell of the p electrons, 3p. So there's only one electron, meaning the answer has to be B. So again, a lot of things had to come together here for us to get the answer. We had to remember that when the period 3 elements, and it's actually really helpful for you if they ever tell you it's a period 3 element, just write all the period 3 elements so you can start crossing them out. It forms a solid oxide. Okay, that crosses out 3 of them because these are all gases and liquids. So we have these left. It reacts with sodium hydroxide and hydrochloric acid. That makes it both an acid and a base. It's amphoteric. Only one was amphoteric. So we write down X is equal to aluminum. And then once we get that, that's not even the answer. The answer has to deal with the electron configuration of aluminum. And we end up with how many p electrons does one atom of X have in the outer shell? It has one electron. So everything from the reactions, the fact that it's amphoteric, to the fact that it creates this anion, to the fact that it's a solid state of matter, and then bringing things all the way back from chapter 1 and 2, figuring in the electron configuration. So it's a very complex question. Let's do one more, but let's look at one from chapter 2. So this is a paper 2, not chapter 2. This is a paper 2 question. The reaction of pure aluminum is only observed if aluminum oxide layer is removed first. Okay. Not really useful information, but when pure aluminum is added to cold water, bubbles of gas are seen. Okay. We knew that. We know the reaction between aluminum and water. And then it says, name one other period 3 element that also produces bubbles of gas when added to cold water. So now we are being asked to go further and actually compare these bubbles, right? So this whole first sentence, this setup, was kind of pointless. Because what they're asking us is, what other period 3 element also produces bubbles of gas when added to cold water? So we're looking for a reaction. This is basically rote memorization. Which element reacted with water in period 3 to create a gas, to create bubbles, right? So if we remember the reaction of sodium with water, when Na reacts with H2O, two things are created. But here's the key. It's cold water. When sodium and water react, it creates sodium hydroxide and hydrogen gas. Those bubbles we're talking about are of hydrogen gas. So this has to be sodium. Now you might be thinking, well, magnesium does the same thing, but you got to remember, magnesium reacts extremely slow with cold water, and so you won't see the bubbles as much. They're very slow, they barely react, they barely see them, whereas sodium will react a lot more quickly, and so the gas is created a lot more quickly. So whenever you're left with a choice of, oh wait, but this also happens, MgOH2 plus H2 gas. Yes, this does actually happen too, but this is fast, whereas this is slow. And here's when we're going to have the conversation of what is a better answer. Sodium is the better answer because the reaction being fast means that we're going to see those bubbles plainly and clearly. Whereas with magnesium, because it's a slow reaction, we might miss those hydrogen bubbles. Those hydrogen bubbles might not happen until 20 minutes later. And so sodium becomes a much better answer. So there are going to be times where you say, wait, but there are two answers. And then you have to ask yourself, what is a better answer? Because there's always a better answer. And if you don't see it right away, start thinking, okay, what could make this answer better? Because it's faster, because it's slower, because it's a more clear color, whatever it may be. In this case, sodium was the only answer they accepted. Sodium is the answer to this problem, not magnesium, because the reaction with sodium is much faster, much more obvious. We will see those bubbles a lot more clearly. That's it. This is it for section 10.8. It is a lot to put together. You have to remember, and as we move through more and more chapters of inorganic chemistry, we are going to see this a lot more and have a lot more facts to remember. So the key here is take it slow, make sure you memorize everything, and make sure you're looking for patterns, not just rote memorization. I'll see you all in the next video to start chapter 11. Thank you for watching.